The surface of the Earth is in constant motion. Ice shelves fracture, rivers flood, and military assets deploy across continents. To track these events, we rely heavily on satellite observation. But the standard satellites we use suffer from a severe physical limitation. They rely on passive optical sensors, meaning they can only capture what is currently illuminated by the sun. This creates a massive blind spot. At any given moment, exactly half the planet is hidden in the dark of night. On top of that, roughly 67% of the Earth's surface is blanketed by thick clouds. If our primary tools require clear weather and daylight to function, we are effectively trying to monitor a complex planet with our eyes closed most of the time. The physical solution to this problem is active sensing. Instead of waiting for sunlight to reflect off the ground, a satellite generates and fires its own energy. By using microwave pulses rather than visible light, radar slices straight through dense atmospheric interference. It ignores thick cloud cover, heavy rain, and complete darkness. But putting a radar in orbit comes with a severe engineering catch. The laws of physics dictate that if you want a high-resolution image, you need a very large physical antenna. To get a sharp, detailed picture of the ground from space using traditional radar, that antenna would have to be several kilometers long. Launching a metal structure that massive is impossible. This is where an ingenious workaround comes in: Synthetic-Aperture Radar, or SAR. Instead of building a physically massive antenna, SAR uses the forward motion of the spacecraft to fake one. As the satellite travels along its flight path, it fires thousands of rapid pulses towards the Earth and records the returning echoes. The system mathematically combines this data. By treating every pulse as a different segment, it constructs a massive virtual antenna in space. SAR trades physical size for complex computation. By utilizing the platform's own velocity, it achieves sharp resolution without the impossible hardware. The raw backscatter data the satellite actually collects does not look like a photograph. To the human eye, it just looks like chaotic visual static. To make sense of it, intense computational algorithms process the overlapping phase histories of those echoes, compressing the scattered static into a coherent, highly detailed image. We steer this radar in different ways. In strip map or scan SAR modes, the satellite drags a wide beam continuously across continents. Alternatively, in spotlight mode, the beam pivots backward to fixate on a single target for the highest possible resolution. But even with this incredibly sharp, all-weather capability, standard SAR still only provides static snapshots of the past. The real world doesn't stand still. If you are tracking moving vehicles or shifting terrain, waiting hours or days for a satellite to orbit back around for another photograph means you lose the target. To capture motion, engineers pushed the processing power further, leading to a technique called video SAR. Instead of processing isolated, single images, video SAR continuously reuses the incoming data stream. It groups the echoes into tightly overlapping synthetic apertures. This continuous data recycling drastically increases the frame rate. It transforms those isolated static photos into a fluid, sequential movie. Video SAR bridges the gap between high-resolution radar and real-time observation, letting us watch dynamic events exactly as they unfold. This SAR image shows exactly how that synthetic vision behaves. Because the radar wave interacts with the physical structure of the landscape, you can see starkly illuminated buildings alongside deep, distinct radar shadows, which can be tracked dynamically as targets move. By comparing these sequential radar frames, a process known as coherent change detection, we can measure crustal shifts down to the millimeter, or track a convoy's exact path entirely through cloud cover, map floodwaters in the dark, monitor supply lines during heavy storms, and observe global hotspots without interruption. By combining the physics of microwaves with the forward motion of a satellite, SAR stripped away the blind spots of weather, darkness, and time, leaving the Earth with nowhere left to hide.